name of Almighty God, I'm Mahsa Sankoshi, and today I want to talk about the dark matter distribution in the galaxy and the universe. As discussed in Chapter 1, the average dark matter density in the universe is non-zero, see equation 111. However, there is much more to dark matter than just this average value because of structure formation. The distribution of dark matter in specific systems differs significantly from the average cosmological value. In particular, in order to interpret the result of direct and indirect dark matter detection, research discussed in Chapter 5 and 6. One needs to the dark matter density distribution (ρx) and the dark matter speed distribution (fx) new in the Milky Way as well as in other galaxies in a variety of other astrophysical systems. Presently, only educated guesses are available for these quantities, with significant uncertainties. In this chapter, we discuss the methods with which such guesses are derived and their results. We start with two general statements which are simple yet at the same time also quite powerful. Dark matter tends to be roughly spherically distributed in gravitationally bound systems. The initial conditions and the structure formation generally predicts nearly spherical distributions. Normal baryonic matter then collapses in the gravitational well, during which it dissipates energy and cools down, resulting in a spinning disk exhibited by many galaxies. See section 2.4. Unless dark matter has similarly large scattering cross sections, it has negligible interactions and thereby negligible dissipation. Neglecting the gravitational effects of divisible matter, dark matter therefore conserves a spherical distribution, so that one can reasonably assume that the dark matter density ρr in astrophysical systems is to a good approximation a function of only the radial coordinates. Or deviations from this rough approximation are discussed in detail in section 2.4. Dark matter is non-relativistic in most systems of interest, and this system of interest is notable exception are dark matter particles in a close proximity of a dense massive body such as neutron star. In such cases, dark matter particles acquire relativistic speeds and can even transfer their large kinetic energy to the star. See, for example, section 6.10.4. For instance, dark matter particles bound to our galaxy must have a velocity below the escape velocity. No escape is almost equal to 500 km per second. Similar considerations hold for other systems such as dwarf galaxies, galaxy clusters, and etc. with the appropriate escape. Going behind the above general statement, rho r and FNU for any given system could in principle be determined in three conceptually independent ways. The first method is observationally by precisely tracing star kinematics in a galaxy or galactic kinematics in a cluster, inferring the underlying gravitational potential and thereby the density and the velocity distribution of matter responsible for the observed motion of the tracers. The next method is via the theoretical methods describing semi-analytically the process of gravitational collapse and its end results. The third and the last one with embodied numerical simulations. In practice, A is too imprecise to provide the full ROR, but it helps in determining the local dark matter density. And the method B faces formal and technical difficulties due to the nonlinear nature of the problem and due to the presence of baryonic physics. Yet it provides valuable insights into the complex processes involved. Therefore, the current most popular approach relies mostly on C with an admixture of other strategies. Usually, this is a two-step procedure. The first step is guess the functional forms of rho or n f nu in terms of minimal number of free parameters on the basis of most often simulations or theory or observations. The second one is determine the free parameters in terms of solid observations of dark matter in our galaxy or in other galaxies. We will present the results of this procedure in section 2.2 and 2.3 for the density and speed distributions respectively. Finally, in section 2.4, we discuss how things can be further refined going behind the dark spherical cow limit. Before doing that, however, it is worth elaborating on the three methods mentioned above. The next section is 2.1 methods to determine the dark matter distributions. 2.1.1 observations. As discussed in section 1.1.1, the basic observation that the galactic rotation curves flatten allows to infer rho r is almost equal to 1 divided by r to the power of 2 at a larger radius r which dark matter dominates. One can use the same idea to try to extract the rho or also at a smaller radius. Objects in circular orbits around the galactic center are essential tracer of the total gravitational potential, hence of the distribution of matter. The mismatch between the rotation curve obtained with such tracers and the one expected from the visible matter in the galaxy must be counted for the dark matter. The dark matter density distribution can thus be obtained by fitting an appropriate parameters function to the total rotation curve. This is often referred to as the global method to determine the dark matter distribution as opposed to the local method discussed below, which is less ambitious and only aim to determine the dark matter density at the location of the solar system and about 1 kpc around it. The method is conceptually simple to obtain the predictions for the rotation curves. The Poisson equation for the Newton potential phi delta to the power of 2 phi is equal to 4 pi ga rho is first solved assuming as a source only the observed mass distributions due to baryons in the stars, and from those in the interstellar gas, rho is equal to rho ab and is equal to rho a star plus rho a gas, taking into account their approximate cylindrical rather than spherical geometry or the theta. The Newton's equations for a test mass in a gravitational field nu to the power of 2 divided by r is equal to minus delta phi divided by the delta r, which is the partial deviation. Then predicts the rotational velocity. Nu r is equal to nu s to the power of 2 plus nu gas to the power of 2 and totally to the power of 1 divided by 2 in the galactic plane at z is equal to 0, where these are measured. Comparison with data for nu r shows that an extra dark contribution is needed in order to reproduce the observations based on the equation 2.1. Nu to the power of 2 is equal to nu s to the power of 2 plus nu gas to the power of 2 plus velocity of the dark to the power of 2, which then allows to determine the dark matter contribution by subtracting the predictions from observations. However, a number of the difficulties arise. First, stellar kinematical data still carry significant uncertainties, both intrinsic to the measurements and due to their interpretation. Also, in the Milky Way, related, for example, to the knowledge of the precise distance of the Sun from the galaxy center and of the Sun's circular velocity. Second, the results of the mismatch fit mentioned above depend crucially on what is being assumed for the visible component of the galaxies. And we have two notes here. Galaxy refers to the both Milky Way as well as to any other galaxy, including the satellites of the Milky Way, for which one is trying to determine the dark matter distribution. The velocity is orthogonal to the galactic plane, and the radial velocities provide extra information in principle. In practice, however, they are not measured well enough. So, more precisely, one has to design a model of the galaxy as a system composed of a bulge, a possible bar, a disk, or gas halo, and possibly even a smaller disk at the core of the bulge. Each of these appropriately modeled using several observation-based configurations. The gas density is extracted, for example, from the 21 centimeter maps, while the smaller models are needed to convert observed luminosity into mass density. The uncertainties on these baryonic morphologies are still sizable, despite the recent improvements due to the fact that data mostly based on optical observations are now being replaced by the near IR data or infrared data, which need only minor modeling corrections. Finally, since the baryonic matter dominates the gravitational potential in the inner few kpc of galaxies, the inner is about 5 kpc for the Milky Way. The contribution of dark matter is intrinsically very difficult to determine in the region. In practice, therefore, observational methods are sufficient to affirm the presence of dark matter in galaxies and to get a rough idea of its large-scale distribution, but are at present not sufficient for more precise determinations. The next method is 2.1.2 gravitational collapse of collision-less dark matter. The formation of a dark matter galactic halo is a conceptually well-defined theoretical problem. Start from a roughly spherical slide over density made of collision-less and dissipation-less bodies and let it evolve under gravity. The system starts collapsing under its own weight, and at some point the inhomogeneity grows beyond the computable linear approximation, but the collapse self-limit without reaching a point with infinite density. This happens because dark matter is collisionless and cannot dissipate energy. So during the collapse, its gravitational potential energy has to be converted into kinetic energy of dark matter particle involved. The sphere therefore eventually relaxes to a self-gravitating quasi-static structure supported by random motion of dark matter particles. The whole process is referred to virialization, and their resulting system is viralized. For example, its energy is distributed between the potential energy V and kinetic energy K according to the Weyl theorem. K is equal to minus 1 divided by 2 V already mentioned in section 1.2. The Weyl theorem provides enough information to estimate the topical scales involved. For simplicity, we consider spherical dark matter over density with homogeneous density of total mass and total ellipsoidal collapse models with non-constant density are also considered in the literature. The main phases discussed below are illustrated in figure 2.1. We define rho eta as a homogeneous density at the instance of turnaround. For example, at the moment at which the overdensity stops following the expansion caused by the Big Bang stalls and turns around to stop collapsing into gravitational bound object. This makes the onset of structure formation. Since dark matter is stalling, its kinetic energy eta vanishes, and thus its total energy eta is equal to eta plus potential eta is entirely due to the gravitational potential energy, and V eta is equal to minus g and integral. The lower boundary is 0, the upper boundary is r. TA is 4p r to the power of t3 divided by 3 rho inside and multiplied by 4p r to the power of 2 dr rho tau divided by r, and after simplification we have a minus 2 divided by 5 multiplied by gm a total to the power of 2 divided by reduced tau, where r is the size of the sphere at turn around and rho in is the density inside the sphere. In our approximation taken equal to rho eta. If spherical symmetry were absolutely exact, for example, if all dark matter particles were following a perfectly radial trajectory, the collapse would have proceeded toward infinite density, forming a black hole. In reality, the system keeps spherical only on average and reaches infinite density thanks to the chaotic motion of dark matter particles interacting only via gravity. After this virialization process, the energy is distributed between the kinetic and potential energy such that the E valorization is equal to chi valorization as a kinetic energy plus V valorization as a potential energy is equal to V valorization as a potential energy divided by 2, where the last equality follows from the viral theorem. Since valorization conserves the total energy, the potential energy via valorization is equal to minus 3 gm total to the power of 2 divided by 5 RF valorization. We still approximate the density as constant. Rho valorization is equal to m total divided by 4 divided by 3 PR to the valorization to the power of 3, where now R valorization is a radius of the valorization halo, therefore implies R valorization is equal to R theta divided by 2. That is, the collapse results in a relaxed halo half of the size of the turnaround bubble with an order of the magnitude higher density. Rho valorization is equal to 8 rho theta. The mean square speed wireless particles is nu to the power of 2 is equal to 2 car valorization divided by m total is equal to absolute V valorization divided by m total is equal to 3j m total divided by 5 r valorization. Solving Newtonian equations for a homogeneous density in an expanding matter dominated universe shows that the average density of the form hollow Roy-Varzation is roughly 200 times the surrounding cosmological density. And you see the figure 2.1 qualitative illustration of the main phase of a nearby spherical gravitational collapse. The dot dash curve shows the result assuming an unrealistic exactly spherical symmetry. The continuous red curves show the realistic result, and the dash curve shows the result within linear approximation, which remains close to the cosmological background bottom black curve. And you see that in the y-axis we have a density as a rho eta and rho valorization, and in the x-axis we have a scale which is reducer inside, reducer to and reducer valorizations. And you see that we have valorizations at a rate curvature, and you see as when we reach to there radius of valorization is about 200 devarizations, and extract spherical is something such as this dash curvature and linear approximation, and finally the cosmological background. So we have this sort of rho is equal to rho average is equal to 3h to power 2 divided by 8 pg is equal to 1 divided by 6 pg t valorization to the power of 2, where t valorization is the time and making the end of the valorizations. Here we use equation CF5, CF7 and equation CF14 for matter domination. Quite often the water radius is thus defined as the radius within which the average density of the hollow is 200 times larger than the cosmological density, and is denoted as R radius 200. The mass inside R 200 is taken as a measure of the total mass of hollow. The reality, at least as seen in numerical simulations, is more involved, but orders of magnitude are correct. Besides its global properties, one can gain a slightly more refined understanding of the final dark matter hollow, in particular its density and speed distributions, in which we are interested here by following analytically the collapse and paying particular attention to the relaxation mechanism. There are several such dynamical processes at play driving the system toward an equilibrium configurations, and the important mechanism for collision-less dark matter particles is the so-called violent relaxation. The energy of an individual dark matter particle changes with time due to the fact that the gravitational potential in which these are immersed generated by the ensemble of dark matter particles themselves also changes with time because of the ongoing collapse. This mechanism works in the efficient way on the short time scales of the collapse, hence the name violent. The total energy of a given dark matter particle divided by its mass. Epsilon is equal to nu to the power of 2 divided by 2 plus v, varies as a derivative epsilon divided by derivative time is equal to delta or partial derivation of phi based on the time. If the gravitational potential is time dependent, the last relation is straightforward to verify the derivative epsilon based on the time is equal to the partial derivation of the epsilon based on the new the multiplication and derivation of nu based on the time plus derivation epsilon based on the phi derivation phi based on the time is equal to nu multiplied by minus delta phi plus 1 multiplied by the partial derivation of phi based on the time plus nu delta phi is equal to partial derivation on nu t, where the equalities follow derivably from the chain rule. The definition of the epsilon from the derivative nu based on time is equal to minus delta phi, which is the Newton's law, or acceleration is equal to force divided by mass for the case of the just gravitational interactions. Whether the particle gains or loses energy is a complex question. One can qualitatively figure out what is going on by thinking of the dark matter particle that starts collapsing from the outstrikes of the halo, which itself will first collapse and then expand until the particle viralize. During the infall, the dark matter particle will dive into a deep potential due to the collapses halo and gain kinetic energy after crossing the center. Unscattered because of its collision-less nature, will climb out of the shallower potential because its few dark matter particles are dispersing and will therefore spend less than the previously acquiring kinetic energy, resulting in a net energy gain. The opposite happens for the particles that starts from inner locations. For instance, a particular or particle at a rest in the center does not move while the proto-hollow collapse. The potential at its center becomes deeper. In general, due to the gain or lose of the energy of a single particle depends on its initial position and initial speed as well as on the distribution of all other dark matter in complex state. The whole process effectively amounts to dark matter particles undergoing many gravitational interactions. As a consequence, their final velocities are given by a sum of many random contributions due to the central limit theorem, which is some sort of the Gaussian theorem energy distribution, which tends toward the Gaussian. If epsilon is equal to n0 divided by 2 p sigma to the power of 2 to the power of 3 divided by 2 multiplied by e to the power of minus epsilon divided by sigma to the power of 2, where the peculiar form of the normalization factor multiplying the exponential will be clear soon. The exponent is epsilon is equal to 1 divided by 2 nu to the power of 2 plus phi, from which is immediately follows the energy distribution. F epsilon can be interpreted as a distribution of the dark matter space. F nu taking the Maxwell-Boltzmann form, F nu is equal to e to the power of minus nu to the power of 2 divided by 2 sigma to the power of 2. The uniform temperature related to velocity dispersion sigma is for a fully virialized halo given by its total mass. To show that, we move next to the discussion of the dark matter density distribution rho for spherically symmetric system. There is a unique correspondence between FNU and rho r, which is a function for velocity and the density of a radius. This general relation is known as the Eddington's formula, and the art of the deriving rho r from a nu FNU as the Eddington inversion. It can be derived by first integrating f epsilon over all velocities, which then gives an implicit expression for the dark matter density distributions. And based on the equation, we have a rho is equal to m. The integral lower boundary is 0, upper boundary is infinite. Derivative of nu for p nu to the power of 2 f epsilon is equal to m. The integral lower boundary is 0 and upper boundary is infinite. Derivative of nu 4p nu to the power of 2 n is 0 divided by 2p sigma to the power of 2 to the power of 3 divided by 2 and multiplied by e to the power of minus nu to the power of 2 divided by 2 plus phi divided by sigma to the power of 2, and after simplification we have a rho 0 e to the power of minus phi divided by sigma to the power of 2, where which rho 0 is equal to mn 0. Equation 2.6 gives the gravitational potential in terms of the rho. Inserting this expression into Poisson equation delta to the power of phi is equal to 4pg rho written in spherical coordinates leads to the derivative based on the radius reduced to the power of 2 radius a derivative based on the radius ln rho is equal to 4pg divided by sigma to the power of 2 reduced to the power of 2 rho to the solution is rho r is equal to sigma to the power of 2 divided by 2 pg multiplied by 1 divided by r to the power of 2. So more precisely, what we are actually dealing with is the distribution function fx nu t defined such that the fx nu t, the third derivative x, the third derivative nu is the probability at time t of finding a particle in the third derivative of x and the third derivative of nu phase space volume center at x and nu. For spherical steady-state system, it can be shown that F depends on x and nu only through the total energy, which is in integral motion. F is said to be ergodic, that is why by integrating epsilon over all velocities, one obtained a spatial distribution of dark matter particles, for example, their number density. The use of the N0 is in the normalization factor in 2.4 was already the first hint for this. Multiplying it by the dark matter mass m1 then obtains the mass density rule. For more details, see for example the chapter 4 in binary and terming. So this distribution is a singular isothermal sphere. The name comes from the fact that this is the same equilibrium configuration characterized by a single radius independent temperature T to which an ideal gas is driven by collision interactions. The role of collisions and interactions is played here by the gravitational scattering between dark matter particles and the whole hollow, with the effective cross section given by the sigma gravitation is equal to gmm total divided by r to the power 2 newton for in our case the quantity that is constant with the radius is the velocity dispersion. Sigma, the correspondence with the case of an ideal gas, is active if one identifies sigma to the power of 2 is equal to chi by t to the divided by m, where chi b is the Boltzmann constant. Summary: the classical theory of collapse of isolated spherical collision-less and dissipation-less systems predicts equilibrium dark matter halos that are singular thermal spheres with exactly Maxwell-Boltzmann speed distributions. This is often called the standard hollow model. In practice, the singular isothermal model is just an idealized approximation. First, the resulting rotation curve is exactly flat. Nu is circular r to the power 2 r is equal to gmr divided by r is equal to 2 sigma to the power 2, which is not what realistic measurements show. Also, its density diverges as r tends to 0, but this is not a dramatic problem since the mass enclosed within the radius r is finite. Mr is equal to the integral lower boundary is 0, upper boundary is r. The derivative of radius for p r to the power of 2 rho is equal to 2 sigma to the power of 2 r divided by g. On the other hand, integrating towards large radius, the total mass diverges, which is absurd from the astrophysical point of view. The profile must therefore be amended and truncated at some large radius. More generally, many effects can cause deviations from the simple picture that led to its thermal distribution. For example, the collapse forces can be incomplete and not reach a full equilibrium state. And the second point is the assumption of a spherical symmetry is easily violated by non-radial deformations in a initial condition. And the third one, the hypothesis that the system is isolated is not valid for hollows embedded in a dark matter cosmic web. Inflows, outflows, and mergers cannot typically be neglected, etc. The standard hollow model can be extended to correct for some of these shortcomings, making it more realistic. Too often at the price of a more involved analytic treatment. See also the discussion in section 2.4. Given these complexities and the limitations of purely analytical approach, numerical simulations have increasingly become an important tool to determine properties of the dark matter hollows. We discuss this next. Now I want to go through another chapter 2.1.3. Results from embodied simulations is a shared method since a statistical mechanism doesn't provide sharp general answers. The gravitational collapse of dark matter is also studied numerically using the embodied simulations, which we already introduced in the section 1.3.2. While such computer codes don't simulate a specific galaxy, we are especially interested in the Milky Way or local dwarfs, but rather an ensemble of more or less typical galaxies. Their results do show that the dark matter hollow density provides tends to possess some universal features as summarized below. Dark matter hollows are produced with sizes that span all simulated scales, from cosmological scales around 100 MPC down to subgalactic scales of tens of PC, ranging about 200 orders of magnitude in the enclosed mass m. The number of hollows n as a function of their mass scales roughly as dn divided by dm is equal to 1 divided by m to the power of 2, and will be discussed analytically in section 2.2.5. And chapter 2 is talking about where dark matter distribution in galaxies and universes. So as you see, the figure 2.2 illustrates subhollows. Embodied simulations find the dark matter forms roughly spherical hollow, which are then surrounded as well as inhabited by many smaller subhollows. From some simulation realized as the MPI and the credit is Max Planck Institution for Astrophysics. To a first approximation, luminous matter follows the distribution of the large-scale structure. For example, galaxies formed where matter is dense. However, galaxies don't trace exactly the underlying dark matter distribution because galaxy formation proceeds with an efficiently that depends on the hollow mass. The relationship between the man over density of galaxies delta Gauss and the mean over density of the total mass delta total dominated by dark matter is complicated. Their ratio, the so-called the bias B is equal to delta Gauss divided by delta total, is in general a function of the scales, the properties of the galaxy in question, and the redshift numerical simulations show that the galaxies preferentially form in halos that are not as too small. Otherwise, supernova feedback hampers the collapse nor too large. Otherwise, gas doesn't cool efficiently enough. Simulations of cold collision lets dark matter produce dark matter hollows, which have in general an ellipsoidal shape rather than being spherical. The non-spherical is limited, however, and is found to be smaller in simulations that include baryons, as we will discuss in section 2.4.1. The subtle assumption of sphericity adopted in the most phenomenological studies is therefore quite reasonable. The density profiles raw of individual hollows computed from numerical data in spherical approximation tend to follow universal slopes. SR is equal to D ln Rho divided by dA ln r that smoothly changes from -1 in the inner region to the -3 in the outer region. For comparison, the isothermal sphere suggested by the analytic considerations in quad equation 2.8 has s is equal to -2. The results of simulations can be fitted by functions such as the ones in the table 2.1, dubbed NFW, from a Navarro-Frank Y to which slope that changes from the -2 to -1 around the radius RS. The INS2 with slope that equals -2 at radius is equal to radius s and continuously evolves. The numerical values of dark matter density profile fit functions for Milky Way will be discussed in the section 2.2.2. The individual gravitational bound objects can be simulated down to sizes about three orders of magnitude smaller than the viral radius or viral defined such that the rho r viral is 200 times larger than the mean density. For reasons discussed in section 2.1.2, the simulation thus cannot resolve a possible core where the density rho becomes constant if it is too small. As a rule of thumb, for a galaxy like the Milky Way, the existence of a core with a size below the one KPC is compatible with the current simulations. In addition to the primary hollow structures, simulations reveal the presence of the numerous smaller subhollows. See Figure 2.2 orbiting between and around main hollows. Their number distribution is dn divided by dm is equal to 1 divided by m to the power of 2, so that the m derivative n based on the L and the m is roughly m independent, that is similar amount of total dark matter mass are stored within objects for any given decade in mass scale, and from the biggest formed structures down to the smallest resolved structures of the order m is equal to 10 to the power 5. Additional smaller halos not yet resolved by simulations are expected to exist, as also anticipated by the analytic arguments to be discussed in section 2.2.5. Simulations show that these hollows possess higher inner dark matter densities and are on average more concentrated than standalone hollows of the same mass. In section 6.8.1, we will discuss how the presence of subhollow boosts the indirect signals of dark matter annihilations. Other features of simulated halos seem less universal. The concentration parameter of any halo is defined as C is equal to R volatilization divided by R minus 2, where R minus 2 is the radius at which the slope reaches S to the is equal to minus 2. R minus 2 is equal to RS in the INS2 parameterization. The mass of the smallest halos, called macrohalo, will be discussed in section 2.2.5. It depends on dark matter particle properties and could, for weak scale dark matter, be comparable to Earth's mass 10 to the power minus 6. Microhollows don't form from merging of smaller hollows. Dedicated simulations suggest that they tend to have a C about 20 up to the 30. The concentration parameter C gradually decreases down to C is almost few for larger objects, galaxies, and clusters, which formed earlier. When the universe was denser, subhollows inside the galactic halos, in particular, have higher inner dark matter densities and are on average more concentrated than the pre-standard halos of the same mass. Moreover, the subhollows are more concentrated the closer they are to the center of the hollow host hollow. Finally, the ratio between the spherical average density and the average radial velocity seems to follow a power law. Rho divided by nu r to the power of 3 is almost equal to 1 divided by r to the power of 1.875. Thank you so much for watching my tutorial video until the end. If there's any simulation for this literature, you can find it from my github.com slash mahsascript slash koshiscript or slash safra script. Today is 17th of the August 2026.